This video is about related rates in the context of calculus, and we'll begin our notes with some general strategies, which will be followed by some examples. First, we're going to be sure to read the whole problem carefully. Then, secondly, we'll probably want to try to draw a diagram if possible. It should include a variable to capture the motion and then recall any applicable geometry that may be required here. So you may need to go back and look up some formulas for area or volume or some other applicable metric for the problem. Then we're going to identify what we know in the problem, which will come directly from the way it's worded. Next, we'll identify what we need, which is usually the question being asked in the problem. And then fifthly, we have to identify when we need it. So I mentioned back in step 2 about the motion that's happening. Typically a related rate problem involves some kind of motion happening in the diagram. Of course, you're drawing a still picture, which is why you use a variable to capture the motion. But then in the problem context, usually you're going to freeze the problem at one particular point, and that's indicated by when you want to find what you need. Okay, so these will all be tied together with the examples we do shortly. And then sixthly, once you have all those pieces, we need to solve using equations which tie together the know, need, and when. And this may involve a derivative. Of course, we're in the context of calculus, and we know those derivative rules, or many of them at least at this point. Let's consider the following example. The radius of a sphere is increasing at a rate of 4 millimeters per second. How fast is the volume increasing when the diameter is 80 millimeters? Okay, so read the whole problem, which we've just done, but that doesn't mean it's always clear. So that's why I like the know, need, when scheme. It just kind of helps organize what's going on in the problem. As stated above, it's always good to draw a picture if we can. This problem involves a sphere, which is a little difficult to draw. We'll do our best to give it a bit of a 3D look. A sphere is like a ball, and of course there's a center to it. And then the distance from that center out to any part of the surface of it is known as the radius, so we'll just label that as r. Now in this problem, we're going to go ahead and write out the scheme know, need, when. And this is a pretty good way to organize most related rate problems. I highly recommend it. We have to understand first what we know. Now in this problem, usually it's given with some kind of numerical value. It says that the radius of a sphere is increasing at a rate of 4 millimeters per second. So we're going to use our calculus understanding. When you see the word rate, that's your clue that there's probably a derivative involved. We've understood derivatives as instantaneous rates of change. And so the radius of the sphere is increasing at a rate of 4 millimeters per second, which means we know that the derivative of the radius with respect to time, so I'll call this dr dt, the radius is increasing here, and that rate happens to be 4 millimeters per second. So I'm going to throw the units in with the number 4. We'll make sure our units make sense by the end. But the point right now is that we know the derivative of the radius, the rate of change of the radius, is 4 millimeters per second. That's what we know. Now, the next part says, how fast is the volume increasing when the diameter is 80 millimeters? Now, how fast is, that's our question being asked, which is what we need to answer this question. How fast is, well, that sounds like a rate kind of question, but this time the question is, how fast is the volume increasing? So increasing, there's the rate language. I'm going to call this dv dt for the derivative of the volume with respect to time. We don't know what that is, but that's what we want. That's what we need to know in this question. And then when, the word when is actually in the problem. That's not always true with a related rate problem, but it sometimes is staring you right in the face. When the diameter is 80 millimeters. Okay, so the diameter, of course, that's the distance all the way across the sphere. We've already labeled the radius in our picture. But that's why we said to use a variable in the picture, because there's motion happening, right? The radius is increasing, which means this ball is expanding outward as the radius increases. But we want it when d for diameter equals 80 millimeters. Now, remember the relationship between diameter and radius? So you have to bring that into this context here. That's a simple geometry understanding. If the diameter is 80, that would mean the radius is 40 millimeters. So they gave diameter in the problem. We have to understand that also to mean radius would be half of that. Now, given what we need, which is the derivative of volume with respect to time, dv dt, we need some kind of equation that's going to pull those things together or put them together. So this is where we have to recall some geometry. And that is, for the volume of a sphere, there is a formula which states V for volume equals 4/3 pi r cubed. So this should come, from the recesses of your geometry experience or whatever you have used in geometry. And again, if this formula is forgotten at this point, you might have to look these things up, but they should be pretty easy to find looking up for volume of a sphere, a cone, any basic geometric shape. So there's our formula for volume, and notice what it includes. It has a V and it has an R for radius. So this is volume in terms of radius. The good news is that's going to help us use everything we have and tie these three things together: the know, the need, and the when. Notice we need dv dt, and we have a formula for v. So the question becomes, well, how do we get dv dt in the picture? The answer is we take the derivative of our volume equation. So I'm going to copy that equation down again and leave a little space around it. So we have v equals 4/3 pi r cubed, but now we're going to take the derivative with respect to time, so dv dt of both sides of this equation. As we've seen using implicit differentiation, this is a common way to write out a derivative. If we then apply the derivative of both sides, the left side will simply mean or have dv dt. On the right side, notice we're taking the derivative with respect to time, that's d dt, but we don't have t in our expression on the right side. We have r, but we're going to understand this to be an implicit form. So we're going to say here, I'm going to put an extra note that says v and r are implicit functions of t. So this is not obvious from the problem, which can be frustrating, but we're going to understand that the volume and the radius are both functions of t, but we're going to understand that implicitly, which will allow us to use our implicit differentiation. To imply this implicit differentiation to the right side of our formula here, our equation, notice the constant of 4/3, that could just be thrown out in front using our derivative rules. The constants come out front. In fact, pi is also a constant, so you could put 4/3 pi out in front and really just apply the derivative of this variable factor, the r cubed. Now remember, r is an implicit function of t, and we are doing a dt derivative with respect to t here, which means we're going to use the power rule, but then the chain rule as well. So we're going to take this 3, that's the power of r, and throw it down in front of the r, making it 3r squared, decreasing the power by 1. That's just the power rule for derivatives. But then given the implicit chain rule, we have to multiply by dr dt. That is the derivative of this inner function, which remember we're assuming is a function of t. Let's take a quick pause and go back to recall what we need and how close we are to getting there, right? We need dv dt. That will answer this problem's question. Well, we have dv dt equal to something, but that something is not simply numerical at this point. There are still variables involved. So we have to go back and plug in what we know as well and when it is. So we'll say dv over dt equals, just copying down everything we have, which would be 4/3, but then really these threes would cancel with the arithmetic in this step. There was a 3 that came down in front of the r for that power rule of the derivative, but then that 3 would cancel with the 3 in the denominator, which means really we just have a 4 in front and actually a 4 pi. The pi is there as well. And then r squared, but r, remember we said we want this when r is 40. Okay, it was actually when d is 80, but we said that really means r is 40. So I'm going to put 40 in for r, which means I have now this 40 squared. And then times dr dt, but that also was given above. That was what we know. If you go back, we know that dr dt was 4. So we can plug in 4 for dr dt there. It's usually a good time, maybe now, could have even done it previously at the previous step or even at the next step, you could do this, but it's always good to consider what the units should be for our answer. And if you connect each piece or understand it, notice dr dt, that was given above as millimeters per second. So we can copy that or just write the units directly underneath of that factor in our result here. And then the radius would also be given in millimeters. So really that's millimeters squared. If you think of that second factor and that third factor having those units, then you're multiplying them together, which means you'd really be multiplying these units together. Well, millimeters squared times millimeters would be millimeters cubed, and then per second would all be over seconds. So you could say millimeters cubed per second is what we're expecting for the units of our answer. And then we can get our answer simply by computing dv dt equal to, and then multiply all this stuff together. Now it's usually the case that you'll leave your answer in terms of pi as an exact result instead of approximating with some kind of decimal. So in this case, if you multiply 4 times 4, which is 16, times 40 squared, it should turn out to be 25,600, and then of course we'll throw the pi in there. So we'll say 25,600 pi millimeters cubed per second as our final result. Remember, we needed the dv dt. If we go back to the start to answer this question, that's exactly what we had just found. Let's try another example. This one says a boat is pulled into a dock by a rope attached to the bow of the boat and passing through a pulley on the dock that is 1 meter higher than the bow of the boat. If the rope is pulled in at a rate of 1 meter per second, how fast is the boat approaching the dock when it is 8 meters from the dock? All right, so there's a lot going on here, but remember, our first step should be to try to draw some kind of picture. You don't have to be an experienced boater to know what's going on here. Let's assume that there's a dock elevated above the water, and let's assume that the boat is flowing in or getting pulled in. The bow of the boat just means the front of the boat, so we'll just do a little cartoon kind of drawing there. There's the front of the boat, and we know that the dock, let's say, is up here. There's a pulley on it, and the rope is attached from the pulley down to that bow or front of the boat. Now, if we read carefully through this problem, we'll know that we could actually put some more things in this diagram. It said, if you look back, that the dock is 1 meter higher than the bow of the boat. Okay, so if this is the bow of the boat, then the dock would be 1 meter higher than it, so we can label 1 meter as the distance between the height of that front of the boat and then where the dock is. We don't know what this horizontal distance quite is, but I'm going to go ahead and draw a triangle, and conveniently this would be a right triangle. Now remember that the diagram should include some kind of variable to capture the motion, but this is where you have to think through what's going on and then look ahead to what we need in the problem, because there's actually a lot of motion going on, right? The rope that's pulling The boat in is getting shorter, but then the boat is also coming closer to the dock. So which of those two motions do we care about? Let's go ahead and get our know and then need when written down. No need when. Panic, there is no need when you use this method. Okay, so the know would be what we have in this diagram, but let's go ahead on to what we need. It says how fast is the boat approaching the dock? So this is where you're going to have to interpret that to know where to put the variable in the picture so that it's most helpful, though there might be actually a couple options for it. Notice that the boat approaching the dock would be this horizontal distance. That's how it is. The boat is not following the rope up to the dock, it's following the water inward toward the dock. So really it's this horizontal distance we care about, which means I'm going to label that with an X just for now. But we also know that the rope is getting pulled in. So I'm going to label that rope something else. I'll just call it R. I wouldn't recommend calling it Y because Y kind of implies a vertical distance and that rope is actually slanted. Now notice it says if the rope is pulled in at a rate of 1 meter per second. That's giving us what we know. But interestingly, we have to be sure to communicate this the right way with the notation. The rope is being pulled in. So think about it. Is this rope getting longer or shorter? Well, if it's getting pulled in, it's getting shorter, which means its rate ought to be negative. So we know that dr dt, r being what I've labeled this rope as, that is actually going to be a negative value, and they say it's at a rate of 1 meter per second, so we'll say -1, and then we'll just say meters per second for that. Now what we need is how fast is the boat approaching the dock. That would be where this x variable is that we've already used. So we need dx dt. And related to what we just said about the rope getting shorter and having a negative rate, we are going to probably expect a negative answer for this because x is decreasing. It's getting shorter. The distance between the boat and the dock is decreasing. So we're expecting a negative dx dt for our answer, but now we know what we're looking for, the dx dt, and we want this when, that, again it says when, the boat is 8 meters from the dock, so that would be the x distance we've labeled. So when x equals 8 would be how we know when to freeze this picture, right? So the variables in the picture capture the motion, but the when condition kind of freezes it and just says, well, when this particular value is true. So though x is decreasing, kind of like take a snapshot when it's 8 and then give me the dx dt at that moment. Now to get things going and find what we need here, which is dx dt, we're going to have some kind of equation to tie all this stuff together. That's one of our steps listed above. So if you look at the diagram, hopefully the geometry is fairly clear at this point that you could use the Pythagorean theorem from this right triangle. That would tell us that x squared plus 1 squared equals r squared. That's just using a simple Pythagorean theorem. Now, there are two ways to go through a problem like this often, and one is to use explicit form and one is to use implicit form. So it may work out just fine to use this form, which would be more like an implicit equation for differentiation. If you wanted the explicit form, you could solve for r. That would tell you that r would be the square root of x squared plus 1, and that would work as well. So, some problems with different equations may lend themselves more easily to one method or the other. Let's go ahead and just stick with this implicit form for now. Now remember, I need dx dt, and that is actually not in my picture yet. I know x is, and I can get t in there by doing the derivative with respect to t of both sides. So I'm going to take d dt of the left side, which is x squared plus 1, and say that equals d dt of the right side, which is r squared. Now remember, we're assuming that the r and the x are implicit functions of t at this point, like we stated in the previous example. So we're going to use implicit differentiation for this, which means for my first term, the x squared, I'll use the power rule, so 2 will come down in front times x to the first. Don't have to write the first there. But then we have to multiply by the dx dt. That would be the chain rule kind of popping out there for the implicit differentiation. Plus, and then the derivative of 1 would be 0. On the right side, same thing with the chain rule here. The 2 will come down in front, making it 2r to the first. Don't have to write the first, but then we have to multiply by the derivative of that inner function r. With respect to t, that's going to be dr dt. Now, this should hopefully make us a little more comfortable with what we have written above, because notice we need dx dt, and now, aha, there it is in our problem. It didn't show up until we took the derivative. And we need it when x is 8. Well, we have x in our problem, so that will be where we plug in 8. But notice what's happening here. We also have an r in this equation that we're going to have to plug something in for. This is where we're going to have to go back and use the explicit form of our equation. Remember our Pythagorean equation? We already wrote this. I'm going to write it again. If you solve it for r just by taking the square root of both sides, you're going to end up with r equals the square root of x squared plus 1. Technically, there would be a plus or minus in front of it, but remember, we're using a positive distance for this rope, so we only consider the positive one. But this will allow us to find what r is, given that x is 8. It'll all kind of fit together in that way, which means we can actually solve for dx dt, which is what we need. Let's take this a step further now and recopy the 2. Instead of x, we're going to put 8. dx dt is what we need, so I'm going to leave that there. The 0 you can ignore now. And then we'll say 2 times r, but instead of r, we're going to plug in 8 for this x value for the r explicit equation we have. This would mean r is the square root of 65. Again, we're just plugging in the x value of 8 to this r equation for the when scenario. So we'll say square root of 65 is going in for r. And then lastly, this dr dt, that's what we had for our no above. That was the -1 value. Notice now what's left. We have everything except dx dt, but that's actually what we need, so we're in good shape. We could just do a little algebra now and say 16 dx dt equals -2 root 65. If we divide both sides by 16, we can reduce the 16 with this -2. We'll end up with negative square root of 65 over 8. And then if you recall back from our diagram, the units for x would be just meters. That was the distance between the boat and the dock. And so our rate for dx dt should be in meters per second is the time measure in this case. So negative square root of 65 over 8 meters per second. Let's try another example. This one reads, a particle moves along the curve y equals 2 sine of pi x over 2. As the particle passes through the point 1/3, 1, its x-coordinate increases at a rate of, okay, there's some key language, a rate of square root of 10 centimeters per second. How fast, there's a good question, how fast is the distance from the particle to the origin changing at this instant? All right, so we're going to need a diagram, which in this case is just the sine function. So let's go ahead and just draw kind of a rough sine graph, or at least a template for one. And then let's also write down what we know, what we need, and when we need it. Now, in this problem, we know several things. The rate of this x-coordinate is increasing at square root of 10 centimeters per second. So we can say dx dt equals square root of 10. You could put centimeters per second there if you want to keep those units handy. Now we also know, as given here, that this particle is moving along a familiar curve. This is 2 sine of pi x over 2. Now you're going to have to bring a little bit of trigonometry back to understand what the basic shape of this function should look like on a graph, because this is going to be our diagram. You'll recall that the 2 in front of the sine function just changes the amplitude. It stretches the graph vertically. And then the pi over 2 inside the input just changes the period. But altogether, the graph for sine will still look roughly like the familiar sine graph, passing through the origin and then increasing and then kind of going through its sinusoidal periodic pattern as it increases to the right. Of course, this is our x-axis and our y-axis. So we have a particle that's traveling along this path. Okay, well, let's go ahead and just put one on the graph. It doesn't really matter where you put it. I'm going to put one down, just a point on this sine function. And from that, we can create some helpful geometry. If I notice, let's go ahead and finish our need and when. So we need, the question is, how fast is the distance from the particle to the origin changing? Well, that distance I will put here in orange, and we have to give that distance some kind of name. But let's also recall that we could create a triangle in this picture to help out where that distance we need is part of the triangle, the right triangle in this case. So if I labeled this triangle in my sine picture here with an x value for its horizontal leg, maybe a y value for its vertical leg, which would be fitting with the way that functions work, then I have to have a name for this distance, and you could say d for distance, or typically math textbooks use s for distance. The benefit of using a right triangle like this is that we can now use the Pythagorean theorem. So here comes our geometry to the rescue. We could say x squared plus y squared equals s squared from our picture, which means we can now say, after giving that distance a name, the orange distance here, what we need, which is what they're asking, how fast is that distance changing? That's a ds dt kind of question. So that's what we need, given that we called it s. And then we need it when we're at this point, given as 1/3 comma 1. So that means x is 1/3 and y is 1. When we're actually passing through the point, that's when we need this. So we can use those values for x and y. All right, so notice if we need ds dt, we're going to have to take a derivative because we don't have that in our picture yet. But we can do a derivative with the equation we've now pulled in. So again, we'll call this ds, or just d dt, the derivative with respect to t of both sides of our equation, which gives us d dt of x squared plus y squared on the left side and d dt of s squared on the right side. This will now be an implicit differentiation using our rules, where again we assume that x is a function of t and s is a function of t. Let's also recall that we actually know what y is. So this was written above in our problem, but y was given as 2 sine of pi x over 2. That just came from the problem. And if that's what y equals, we're going to have to use that and plug it in for this y variable here. But we assume that x and s are both functions of t implicitly, and then go forward with our implicit differentiation. Let's rewrite this one more time before we dive in with the derivative so we can replace y with what it equals here, which will just get us ready to go. So I'm going to recopy this as d over dt of, we have x squared plus y squared, but instead of y, we're going to put 2 sine of pi x over 2, because that's what y is, as we've stated. And that will be squared. So there's x squared plus what we replaced with y there, squared, equals d dt of s squared. Again, we're now assuming that s and x, which are the only variables present in what we have, are both implicit functions of t. If we go through each term and apply our implicit differentiation, assuming that x and s are both functions of t, then we'll start here with the x squared. It would turn into a 2x and then dx dt. Remember, that's the chain rule. Popping out here, where we multiply by the derivative of the inner function, which is x, assuming it's a function of t, so dx dt it is there. Now moving on to the next term, which is this it was y squared. We replaced the y with the 2 sine of pi x over 2. That's all squared. So the derivative of that term could involve several things. We'll use the power rule to throw this 2 for the square down in front to make this plus 2. And then we'll keep the inner function as 2 sine of pi x over 2, and now that would be to the first power, which we don't have to write. And then we would have to multiply though. So here's the chain rule, right? The 2 came down in front. Now we have to multiply by the derivative of this inner function, which would be 2. And then the derivative of sine is cosine. Keep the inner function pi x over 2. But then we multiply by the derivative of that inner function, which would just be pi over 2 dx dt, again assuming x is a function of t here. That's using the implicit differentiation for it. And then finally on the right side where we had d dt of s squared, that would be 2s, and then ds dt, again assuming s is a function of t implicitly. Now we'll go back carefully and see what we can plug in from what we already have. So I'll start over and say 2, and then instead of x, we'll plug in 1/3. That was from what we have in the when above. Remember, x is 1/3, y is 1. So x is getting plugged in as 1/3. dx dt comes from what we know above, and that is given as the square root of 10. We're just plugging in one piece at a time here. We'll continue on. Now, there's a lot of kind of messy arithmetic going on as we look at the rest of this. Notice all these 2's. There's a 2 times 2 times 2. Really, all those 2's could be put together to be 8. And then we have a sine of, now it's pi x over 2, but again, if x is 1/3, then that really means pi over 6. And then we also have cosine of the same thing, which would be again pi over 6 when x is 1/3. And then we're multiplying by pi over 2 and then dx dt, but again that is the square root of 10. And so we can plug those or that in for dx dt. And this all equals, of course, 2s ds dt. Okay. So we're getting maybe closer. Let's go back and make sure we're still pointing in the right direction. If you go back way up to here where we had written our know, need, and when, we already plugged in dx dt as square root of 10. That occurred a couple times in what we have. We need ds dt. Okay, well notice we have it. It's not alone yet, but at least we have it in the picture. But if you look through the rest of what we have, it's all numeric except for one more thing, this s that's in front of the ds dt. But if you recall what we had said above, we already said that s squared equals x squared plus y squared from our Pythagorean theorem, from the triangle we had in our diagram. Okay, so if you plug in x and y as we know them, of course x being 1/3 and y being 1, and then solve for s in this, we should get that s is the square root of 10 over 3. Okay, there's a little bit of arithmetic involved with that, not terrible, so go ahead and try that out. But that should be what our s value is, which is what we can plug in for the s that we have remaining. Alright, so to save some space, let's actually go back right here and replace the s with the square root of 10 over 3 that we just computed, and then get rid of all this so we can use this space. But we're working our way toward finding what ds dt is, and we have it in our picture. We just need to get it alone now. So let's do a little more cleaning up for this. In the first, if we go all the way back to the left side, this is really 2 root 10 over 3 plus, and then moving forward, I can reduce a little more here by canceling this 2 that's underneath the pi and the 8 that we had computed in front. 8 over 2 is really 4, so I could call that 4 times, and then sine of pi over 6, we can just turn that into an actual trigonometric value. The sine of pi over 6 is really 1/2. Refer back to the unit circle if that's a little fuzzy. And then moving on, the next factor is the cosine of pi over 6? Well, that's square root of 3 over 2. Again, refer back to the unit circle as needed for that. And then we have times, now we've already canceled this 2 with the 8 to get the 4. So that 2 is really gone, which means we just have pi square root of 10. And then that's equal to this 2 root 10 over 3, and then ds dt. Okay, let me flip some things around here. We're trying to get ds dt alone. We have it, and we can get it alone by dividing both sides by this 2 root 10 over 3. So really, let's say ds dt equals the reciprocal of that, so 3 over 2 root 10 times the entire left side of what we had above, which is really 2 root 10 over 3 plus, and then notice what's happening here. We can cancel some more. These 2's in the denominators would cancel with the 4 that's above them, giving us really just the square root of 30 and then pi, if we multiply those square root of 3 times the square root of 10. If we then distribute this 3 over 2 root 10 into both terms to get ds dt alone, turns out we'd end up with 1 plus 3 root 3 over 2 times pi. You can check out just the arithmetic of distributing this inside, that's all that is. And then the units for this would be centimeters per second. Let's try another example, which says a trough is 10 feet long and its ends have the shape of isosceles triangles that are 3 feet across at the top and have a height of 1 foot. If the trough is being filled with water at a rate of 12 feet cubed per minute, how fast, there's a question, is the water level rising when the water is 6 inches deep? All right, so let's try to get a picture going on. You don't have to be an artist, but sometimes it can be tricky to draw some of these 3D figures. So we'll draw a triangular trough, which is what this picture was, or this problem was indicating. And so it's kind of, opening upward, filling up with water. And we're going to have to bring in some geometry to this. But of course, let's start with the know, need, when, to make sure we're all pointing in the right direction here. Now, we know that the water is being pumped in or filled, right? It says it was filled with water at a rate of 12 feet cubed per minute. So that's actually a volume metric, a cube like that. So we know that dV dt, the volume of this trough, the water of it, that is, would be positive 12, and that's feet cubed per minute. So we know that. Now, what we need is, they say, how fast is the water level rising? Okay, so we haven't really labeled much in our picture yet. That's what we're going to have to start to do to get a handle on which variables to use. The water level is the distance from the bottom of the trough to where this water is, and why don't we just call it h for height? I mean, you could probably use any letter you want there, but let's just use h. You might get away with a y, but I like to reserve y's and x's for like coordinate things. So let's use h for the height, which means we would need a dh dt. How fast is the water level rising? It's a rate kind of question. When the water is 6 inches deep, that would be when h equals 6. Except we have to be careful of one thing in this problem, and always look out for this. Notice the units that are being used, and they actually mix and match some in the way this is written. When the water is 6 inches deep, but the other measurement was given in feet, both in the volume and in the height. So we have to be careful not to mix and match those. Instead of saying 6 inches, we really should say 0.5 feet. So we're just kind of correcting the units there so that they match in the problem. Now let's bring in some geometry as usual, right? And find that the volume of this water trough, which is really what's called a triangular prism, kind of goes down the whole thing. Okay, we're looking for this 3D triangular prism, and we want the volume of it. The volume of such prism is really the area of the base times the height, but the height in terms of a prism really means the distance from one side of it to the other. So in this case, we'll say V for volume is area of the base, which we don't know yet, times the height, but the height is given in the problem as 10. If you go back up and read, it said that the trough was 10 feet long, given in the problem, so really we could label 10 as the distance all the way down this trough. So that's what's known as the height of a prism if you're stretching out this triangular prism here. Now what we have to figure out is the area of the base, which by the way is like this water triangle that we see at the end of our trough. To do that, we're going to have to redraw this to be super clear in 2 dimensions. So I'm going to draw just like if I was looking straight at the side of this trough, it would look like this kind of triangle, and then there's the water level kind of cutting through it. Now we've already labeled the height from the bottom of this trough to that water level as h. We also were given in the problem above that the entire height of the whole trough, not just the water, but the whole trough, is 1 foot. And we were given that the height, or the length across the top, was 3 feet. So those aren't negotiable, those were just given in the problem above. But now in order to find the area of this base, this triangular water base, which is what we're looking at here, just in 2 dimensions here, we have to know that the area of a triangle is 1/2 base times height. Well, the base of this now shaded in triangle, we need another name for. That's the length across where the water is. I'm going to just call that B, because then we're going to have to utilize some geometry here with similar figures. Now again, this geometry may be a little rusty, but it's not terrible. We can use a proportion to say that the measures of the larger triangle, that is the entire trough here, where I say the distance across, which is 3, over its height, which is 1, should be proportional to or equal to the same metrics for the smaller shaded in water triangle here. So that would be the distance across, which is B, over its height, which is h. Now if you cross multiply this, you'll get 3h equals B, which will help us put this all together, because remember, I want the area of the base of my triangular water prism going all the way through. Well, the base is a triangle, so that'd be 1/2 times the triangle's base, which is B, times the height, which is h. That is the height of this little 2-dimensional triangle. We've already labeled that as h, okay? And then it's that's the area of the base. The base happens to be a triangle. The formula for the area of a triangle is 1/2 base times height. The confusing thing is that there are 2 heights in this scenario. We have the height of the little triangle, which we've already used now and labeled as h, but then we have times the height of the prism, which we already know is 10. That's the distance between the 2 triangular bases in the 3D object. That's the distance all the way down. So that can be confusing. There are 2 different heights. But our other problem is that we now have 2 different variables, a b and an h, in what we have for our formula, but we want only one of those. That's where we're going to use this other equation we got from the proportions to rewrite this as v equals. Now we can multiply some stuff together here. The 1/2 times the 10 will give us 5. And then really, if b is 3h, then I can say this is really 3h times h, just substituting 3h for b, which means v equals 15h squared. And now finally, we have a formula for volume in terms of a single variable h. If I now apply the derivative with respect to t to both sides, so d over dt of the left side v equals d over dt of the right side, which is 15h squared. Okay, now we're going to assume that h is an implicit function of t, like we've been doing with these related rate problems here. And this would tell us that dv dt equals the derivative of the right side here, assuming h is an implicit function of t, would be multiply the 2 down in front for the power rule to get us 30h to the first power times dh dt. So now the good news is dh dt is actually what we're looking for. That's what we need. And dv dt is something we know above. So we can put this all together now to say dv dt was 12. So 12 equals 30 times h. Now h, remember, we converted that to feet already above. That was 0.5 feet. And then dh dt. If we solve for dh dt, of course, there's just some arithmetic involved here. We could say that dh dt equals 4/5, and that would be feet per minute for what we needed there.